All right, so this is my dad. Daniel Grayson. He's a math professor. He's a math professor at the University of Illinois, and now he's mostly retired, but he still does work at the Institute for Advanced Study in Princeton, where he's working on mathematical proofs. He also was one of the founding developers of Mathematica, and he also wrote Macaulay 2, which is this research mathematics program. So he's going to talk about checking proofs of computers. Yep.
Okay, thank you for the invitation. Okay, I'm a mathematician. There are lots of mathematicians. They're all human, and they all make mistakes. And what they do is they publish 100,000 math articles per year. So far, there are 3 million of them that are indexed. And this is a collaborative activity. Each math article typically refers to 10 to 20 to 30 other math articles, pulling in the theorems that it needs to use to prove further theorems. And when there's a mistake in one of the papers you're using, that means maybe your theorem is no longer necessarily true. There are lots of papers where there are probably mistakes. And it'd be nice if we reached a new age of mathematics where every proof we publish is certified to be correct before it's even submitted to the journal. So working toward that goal is what I've started learning how to do, and I want to tell you a little bit about that. So formalization of modern mathematics, that's what we want to do. Now, one thing about formalizing proofs in mathematics is that one application of that is verification of code, because what you want to typically do about code is to prove a theorem about it. Now, the traditional way of checking mathematics is with set theory. There are things called sets, and there are things called propositions, and there are some axioms about the sets there are about 10 of them, and mathematicians refer to these axioms implicitly every time they write a paper. But the new approach, which mathematicians are not really cognizant of, but which arises out of computer science departments where people study programming languages, is called type theory. It's actually not very new. It got its start in 1908 with mathematicians, but it's been developed by computer scientists into something wonderful. As an example, the four-color theorem was checked 10 years ago using type theory. The proof was originally published in 1976, but it turned out to have errors. And errors kept cropping up every few years. So there were thousands and thousands of cases, and occasionally someone would point out that a case had been omitted. So type theory is something that programmers should be acquainted with, because the word type here means the same sort of thing that's called a type in some programming languages. When you declare a variable in C, you give the type of the variable. Type theory is interesting for mathematicians also because it gives more meaningful types for mathematical objects. It's sort of odd to think of the number 3 as being a set. What are its elements? Is 2 an element of 3? Well, it doesn't really matter. That's not the sort of question mathematicians really want to consider. And the point of passing the type theory, one of the points for me at least, is that these sort of irrelevant questions can't even be phrased in the language. They're just not syntactically allowed. It's another advantage of type theory over the previous system is that it's a complete formal language. There's a syntax. Everything is completely specified. The computer programmer should be right at home learning the new syntax. I'm not going to show any syntax today. I don't have time. The cool thing about it is that when you write a proof, you're writing the body of a subroutine. You're certifying your code as you write it. And another cool thing about it is that proofs turn out to be first-class objects, and you can refer to them and use them in later proofs. Now, how does it really work? I'm just going to give a brief indication. In 1889, Giuseppe Peano proposed axioms for arithmetic, axioms for the natural numbers. And there were a handful of axioms, but the basic idea is that you introduce the natural numbers by saying that there's a natural number called 0, and then you say that whenever you have a natural number, there's a successor to it. So the successor of 2 would be 3, the successor of 3 would be 4, and so on. And then you introduce a logical rule called the principle of mathematical induction, which allows you to prove theorems and define functions. But a computer programmer would like it. The functions that are defined by mathematical induction are the same as the functions that you can code in a programming language as a recursive function. You're accustomed to doing that, for example, with the factorial function. A proof by induction is the same sort of thing. It's a proof by recursion. You call the proof inside yourself and you look at cases. And so the idea with proving a theorem by induction is that when you have a variable of type natural number and you're trying to prove something about it, there are 2 cases to consider. Either it's 0 or it's a successor of something. And if you can prove the theorem in those 2 cases, then you've proved it in every case. So think of the Ruby case statement, for example. Now, what is really cool about the new system is the treatment of equality or identity. I'm going to call it identity today because it's a little bit different from the way equality works. Equality is defined in a way similar to the way Peano introduced the natural numbers. It's you postulate that when you have 2 things of the same type, there's a new type that describes when they're equal, x equal y. And so you postulate that x equal y is a statement that you may or may not be able to prove. And there's basically just one way of introducing a new proof of the form x equals y, and that is when you have an x and you introduce the so-called trivial proof that x is equal to x. So giving a proof by induction about equality involves examining cases. It's easier than with the natural numbers, where there were 2 cases to consider. There's just 1 case. That's the case where it's trivially equal. And so that makes equality a really strong logical notion and allows you to prove lots of things about equality. For example, the first thing you might try to prove is that equality is a transitive relation. If x is equal to y and y is equal to x, then x is equal to z. You reduce that to the case where z and y are the same thing. So there are 2 aspects to the new world, and here are the buzz phrases that are associated with them. There's homotopy type theory, and there's the univalence axiom. So in homotopy type theory, remember I said the proofs are first-class objects. You might have 2 proofs that x is equal to y, and then you can consider whether they're equal. And they might not be. So this is the thing that's very strange about the new world, and this is what computer scientists didn't know how to handle until within the last 5 years. And it leads to a really interesting world where the old world of set theory is embedded in the sense that the old notions of set and proposition have definitions in terms of the new notion of type. And for me, what this means is that the notion of type is a deeper, more fundamental notion than the old notion of set or the old notion of proposition. And then these proofs that x is equal to y, there's a geometric way of visualizing that. You can think of x and y as 2 points in space, and you can think of a proof that x is equal to y as being some path that gets you from x to y. And then there's the univalence axiom, which makes equality stronger than you might think. Remember I said the only way of introducing a new proof of equality is when you have one thing and you have the trivial proof that it's equal to itself. Well, the univalence axiom introduces new proofs of equality other than the trivial proof that come from bijections, as we saw in the previous talk. So if you have a bijection from a 5-element set to a 5-element set, it gives you a proof of equality between that 5-element set and that same 5-element set that embodies the bijection in some way. And somehow what happens by virtue of this univalence axiom is that the bijections are promoted into this very strong notion of equality. I already told you proofs about equality are really easy to construct. And so all the distracting statements go out the window, like whether 2 is an element of 3. Proofs can be transported to equivalent situations that amounts to reusing your code, and it also introduces a new foundation for mathematics where somehow this fundamental notion of type, which is more fundamental than set, can actually be studied in its own right. So here's some links to various things that are happening out in the world. These slides are out there. There's the website, there's the blog, there's the book. And maybe I'll just show you the book. There's the book. You can buy it you can download it for free. It was a collaborative project among the 40 people at the special year last year. And it's a 600-page textbook about the new theory. And the people who wrote it are standing there. Thank you very much.
So we should have we should have a few minutes for questions because it hasn't been 15 minutes yet. So yeah, you can get set up, Russ.
A question which is, has this become sufficiently mainstream that basically every paper is expected to have an appendix that shows that the proofs are valid?
That's sort of the long-term goal. And by no means is it mainstream now. This is fringe. And I'm one of the few research mathematicians without a background in formal logic or computer science who's studying how to do this. And actually, I think it's a little bit premature. There are lots of things about the software in which this is implemented, and even about the basic choice of what exact sort of type theory you want to introduce. The choice of it has to be decided and optimized. There are all sorts of proposals, and so a lot of what these people are involved with is thinking about the foundations of these foundations and whether it's the best and how to improve the computability properties of it. This univalence axiom actually is missing a desired computability property, and that something really has to be done about that. So, no, I think it's a long-term goal. It'd be nice if there'd be many proofs 5 years from now, many papers 5 years from now that would have proofs. And on the page of links, I pointed to a paper I wrote in October, where my project since December has been to try to check the proofs in that paper. And so it's hard going, and I hope to learn about how to improve the system as I work on it.
I thought it would be good to mention you mentioned the 4-color theorem, and I thought I would just explain what that is. Basically, the theorem says if you have 4 colors of paint, that is enough colors to color in a 2-dimensional map of the world, no matter what the country boundaries are. So you can color every country with a different color, and it's not touching the same color. And you said that proof was checked by computers, and it was very complicated, and it was hard for a human to check. So that's cool. Any more questions?
I guess this is more elementary. Can you give an example of like math types that because in programming we think of types are like floats, integers. Like what's the difference between the types you were describing in like that programming type?
Well, it's the same exact sort of thing, except of course an integer would be an idealized integer, unbounded. And but also the part of this theory is the ability to make new types from old, and to have all of your functions and subroutines typed in a very strong sense. And so in particular, if x is a type and y is a type, then you should be able to make the type of functions that accept an argument of type x and return a value of type y. And even more, suppose you have a type y, a function from x to types. Think of y as varying depending on the value. And then you should be able to declare that your function accepts an argument of type x and returns a value not of a constant type y, but of a variable type y that depends on the value of the input parameter. And so that's how you accommodate statements that are theorems. A theorem of the form, for all x, something about x is true, is given by a proof, where the proof is a function that accepts a proof of, accepts the argument x of type capital X, and then constructs a proof of the desired statement. And the desired statement depends on what x is. So, but the traditional types you know and love, like structs and unions, are there. They correspond to and or.
All right, I think we should move on. Thanks.